In section R.3, we look at roots, radicals, and rational exponents. Let's first define the nth root of a. If n is a positive, even integer, and a is a non-negative real number, then the nth root of a denotes the non-negative number whose nth power is a. If n is an odd positive integer greater than 1 and a is any real number, then the nth root of a denotes the number whose nth power is a. The number nth root of a is called the nth root of a. This symbol is called the radical, and n is called the index, and if there is no n present, we call it a square root. So let's just make sure we have the basic concepts covered here. So we want to determine the cube root of 64. Well, the cube root of 64 is 4. The reason is because 4 to the third power is 64. So 4 is the number that you have to multiply by itself 3 times to get 64. And so that's what this is basically asking. What is the number we multiply by itself 3 times to get 64? The fourth root of 16? The fourth root of 16 is 2. Why? Because 2 to the fourth power is 16. And for the third one, the fifth root of negative 32 is negative 2, because negative 2 to the fifth power is negative 32. So when we say the nth root of a is equal to some number, let's say b, the definition of this is b to the n power must be equal to a. Let's talk about rules for operations with radicals. These are the two most important rules. The first one's called the product rule. The product rule says if you have the nth root of a multiplied by the nth root of b, this is the same as the nth root of a times b. The quotient rule is the same thing, but for division. So the nth root of a divided by the nth root of b is the nth root of a divided by b. And for the second one, we assume that b is not 0. So as an example, let's talk about rationalizing the denominator. So in the first problem here, we have the square root of 18 over 5. Using the second property there, we can rewrite this as the square root of 18 divided by the square root of 5. And rationalizing the denominator means that we want to get rid of the radical in the denominator. And to do this, we have a trick. We can multiply by the square root of 5 to the top and to the bottom. When you do this, you get the square root of 18 times 5, which is 90, and the square root of 5 times 5, which is the square root of 25. Now the denominator becomes 5 because the square root of 25 is 5. And in the numerator, we can simplify this. We can break this down as the square root of 9 times the square root of 10. Now the reason I choose the square root of 9, of course, is because it is equal to 3. So in the final analysis here, we get 3 times the square root of 10 divided by 5. And so we have rationalized the denominator because we no longer have a radical in the denominator. As a second example, consider the cube root of 10 over the cube root of 3. And we want to do the same thing. We want to get rid of the radical in the denominator. Now for this one, it's a little bit trickier. What we have to do here is we have to multiply the top and the bottom by the cube root of 9. Now why the cube root of 9? Well, because when we multiply the denominator here, we need the inside to be a perfect cube when we multiply it. 3 times 9 is 27, and 27 is 3 to the third power. So when we multiply this together, we get the cube root of 90 on top, and we get the cube root of 27 in the bottom. And then from there, we're going to simplify. The cube root of 27 is 3. And on top, we have the cube root of 90. Now the question is, can we simplify the cube root of 90? Well, only if a factor of 90 exists that is a perfect cube. But if you think about 90, 90 is 9 times 10, 9 is 3 times 3, and 10 is 5 times 2. If you put all these factors together, you'll notice that we do not have a perfect cube because we don't have 3 of the same number. So what that means basically is that this is simplified. There's nothing else we can do here. Let's talk about finding the nth root of a to the n. So if n is odd, the nth root of a to the n power is just a. So basically what we're saying there is that if you have the nth root of a to the nth root cancels out the nth power and you just get the number a. But if n is even, we have to be a little bit more careful. If n is even, the nth root of a to the n is not a. It's the absolute value of a. And the reason it's the absolute value of a is because if the power of a is even, then a to the n will be positive even if a was a negative number. So as a quick example, notice that the cube root of negative 4 to the third is negative 4. So what's happening here is the cube root and the third power are canceling out. However, when you have an even power like you have here, the square root of negative 4 to the second power is not negative 4. It's positive 4. Now, if that's still a little bit confusing, let's just think about why this is the case. If you do it a different way, negative 4 to the second power is positive 16. And we all know the square root of 16 is positive 4. So when we have the square root of negative 4 to the second power, it would be incorrect to cancel the square root and the square and say the answer is negative 4. That's simply not true. So when you have an even power and an even root, you have to use absolute values. All right, let's take a look at a couple of other examples. Let's take a look at a couple of examples. Here we want to simplify the following. In the first problem, we have the square root of 75. The way we're going to simplify this is we're going to take the number 75 and we're going to break it down into what its factors are. So we know that 75 is 25 times 3, and we know that 25 is 5 times 5. So if we look at all the factors of 75, we can see that it is 5 times 5 times 3, or you can think of that as 5 to the second power times 3. So the square root of 75 is the same as the square root of 5 to the second power times 3. And if I break this apart into the square root of 5 squared times the square root of 3, we can now simplify this because here we have a square root and a second power. So technically what happens here is we get the absolute value of 5 according to this property, right? Because we have an even root and an even power, multiplied by the square root of 3. However, the absolute value of 5 is 5, so this simplifies into 5 radical 3. For the second one, we have the cube root of 125 over 108. And so to simplify this one, we need to think about the factors of these numbers. Well, 125 is 25 times 5, and 25 is 5 times 5. So 125 is actually a perfect cube. It's 5 to the third power. For 108, we need to break it down. 108 is 54 times 2, and 54 is 27 times 2, and 27 is 9 times 3, and 9 is 3 times 3. So the prime factorization of 108 is 3 to the third power times 2 to the second power. All right, so now let's see what we can do with this problem. So we have the cube root of 125 over 108. We can rewrite this as the cube root of 125 over the cube root of 108. And this can be expressed as the cube root of 125 is 5 to the third power and divide that by the cube root of 108 is 3 to the third power times 2 to the second power. And so in the numerator, we have the cube root of 5 to the third. That's just going to turn out to be 5. In the denominator, we have the cube root of 3 to the third times the cube root of 2 squared. So to simplify this, notice that the cube root and 3 to the third, those cancel out. So we get 5 over 3 times the cube root of 2 squared is 4. All right, so we've simplified it, but notice we still have a radical in the denominator. So to get rid of that radical in the denominator, I'm going to now multiply by the cube root of 2. Now, why the cube root of 2? Well, it's because the cube root of 4 times the cube root of 2 is the cube root of 8. And in the numerator, we're going to have 5 times the cube root of 2. And the reason I chose to do this is because the cube root of 8 is equal to 2. And so in the denominator here, we have 3 times 2, which is 6. So in the end here, we get 5 times the cube root of 2 divided by 6. And that's the complete simplification of that one. Now for the third problem here, we have the square root of x to the 5th times y to the 7th. Now to simplify this, we're going to rewrite this as the square root of x to the 4th times x to the 1. So that's x to the 5th. And then y to the 7th is y to the 6th times y to the 1. Now you might have the question of why did I select to break it down in this way? Well, we have a square root here. So what I'm trying to do is find the largest even number that divides into 5 and 7, or that is less than 5 and 7, and that's 4 and 6. Now, why am I doing that? Well, we can rewrite this as a square root of x to the 4th is x squared squared. Y to the 6th is y cubed squared. And then we have x times y left over. That's these two factors here. Now, the reason this is nice is because I can break this down into the square root of x squared squared times the square root of y cubed squared times the square root of xy. And what happens here is this square root and this square power cancel out. And technically, you should be getting the absolute value of x squared times the absolute value of y cubed times the square root of xy. However, you'll notice in the problem, they say to assume that x and y are positive numbers. So because x and y are positive numbers, we don't have to keep the absolute value here in our answer. So our final answer is going to be x squared y cubed times the square root of xy. Next, let's notice what happens when we take an expression like the square root of a plus the square root of b, and we multiply it by the square root of a minus the square root of b. So we can use the FOIL procedure or the distributive property, and ultimately in the end here we get radical a times radical a, which is what you see here. And then we get radical a times negative radical b, which is what you see here. And then we have radical b times radical a, which is this. And finally, we have radical b times negative radical b, which is this. And what's really nice about this is these middle terms here cancel out. These are opposites of each other, and so they just simply cancel out. And we end up with radical a times radical a minus radical b times radical b. Well, radical a times radical a is a, and radical b times radical b is b. So you end up getting a very nice expression, a minus b. Now, what's really going on here is these expressions have a relation to each other. So radical a plus radical b and radical a minus radical b, these are called conjugates. Notice that the expressions are basically exactly the same, except that these signs here are opposites of each other. And anytime you multiply these conjugates with square roots, the radicals are always going to go away. So when you get to a problem like the fourth example here, where it says to rationalize the denominator. So again, what that means is we want to get rid of the radical in the denominator. So what we can do to accomplish this is we can multiply the top and bottom by the conjugate. And the conjugate of 4 minus radical 2 is 4 plus radical 2. Now, when we multiply this out, we're going to FOIL in the denominator. So let's go through this. 4 times 4 is 16. Then we have 4 times radical 2, which is positive 4 radical 2. And then we have negative radical 2 times 4, which is negative 4 radical 2. And finally, negative radical 2 times positive radical 2 is negative 2. And I think I should say something about that real quick. There's a shortcut. Anytime you have radical A times radical A, that's always just going to be A, right? So radical 2 times radical 2 is 2. In the numerator, we're also going to distribute, but we're going to simply multiply 5 times 4, which is 20, and 5 times radical 2, which is positive 5 radical 2. And now when we simplify, notice what happens in the denominator. 4 radical 2 and negative 4 radical 2 cancel out. So in the numerator, we have 20 plus 5 radical 2. In the denominator, we have 16 take away 2, which is 14. And this is our answer. The reason this is our final answer is because there's nothing that we can cancel out. There are no common factors among all three of these numbers. Next, let's talk about combining radical expressions. So to combine radical expressions, you have to have like radicals. So as a quick mini lesson on this, if you have 5 radical 3 plus 4 radical 3, this would be 9 radical 3. So we're just adding 5 and 4 to get 9. That's the basic concept. Just another quick one. If you have 5 times the cube root of 2, take away 8 times the cube root of 2, this would be negative 3 times the cube root of 2. So if you have like radicals, which means they have to have the same index and the same number on the inside, you can add or subtract the radicals together to combine like terms. Now let's take a look at these examples. So in the first problem, we have the square root of 48 plus the square root of 27 minus the square root of 12. And to simplify this, notice that none of these radicals are alike. So what I need to do first is simplify the radicals. So the square root of 48 can be rewritten as the square root of 16 times the square root of 3, which is the same as 4 square root of 3. Square root of 27 can be rewritten as square root of 9 times the square root of 3, and that simplifies into 3 square root of 3. We're going to be adding those together. And then finally, square root of 12 is the square root of 4 times the square root of 3, which is 2 square root of 3, and we are subtracting that. So now notice that all of these radicals are square roots of 3s. So we can add these together. 4 of them plus 3 of them is 7 of them, minus 2 of them is 5 of them. So our final answer here is 5 radical 3. Now for the second part of this, we have 3 plus radical x multiplied by 4 minus 2 radical x. So what we're going to do here is just the FOIL procedure. We're going to multiply this out. 3 times 4 is 12. Then we have 3 times negative 2 radical x, which is negative 6 radical x. And then radical x times 4 is positive 4 radical x. And finally, we have radical x times negative 2 radical x, which is going to be negative 2x, right? Because radical x times radical x is x. Now we combine like terms in the middle. We end up getting 12 minus 2 radical x minus 2x. And that's as far as we can take this. Next, we talk about rational exponents. Rational exponents are just another way to talk about radicals. So we'll just start with a basic definition. The expression a to the 1 over n power simply means the nth root of a, as we have defined it earlier in this section. So when you're evaluating something like 27 to the 1/3, we just have to know that 27 to the 1/3 really just means to take the cube root of 27. And that, of course, is equal to 3. Likewise, negative 36 to the 1/2. Well, 36 to the 1/2 is the square root of 36. The negative is not a part of that because there are no parentheses around this, right? If you have parentheses around this, then the negative would be on the inside. But since there are no parentheses, the 1/2 power only applies to the 36, not the negative sign. So for that reason, the negative is outside of the radical. And so this is simply negative 6. Now we take the definition a little bit farther. If you have a to the m over n power, what does this mean? Well, the bottom number of the fraction is the root, and the top number of the fraction is the power. So a to the m over n can be thought of as either the nth root of a to the m power or the nth root of a quantity to the m power. And it doesn't really matter which way you do it. Now, secondly, I just want to remind you all that all of the properties that we talked about earlier regarding exponents, these are all true even if these numbers are not integers. So all of these rules that we have here are the same as what we talked about before, but now it applies to even rational exponents, not just integer exponents. Let's take a look at some examples. So in the first example, I simply want to evaluate the expression 4 to the 3/2 power. So there's a couple of different ways to do this. And I like to write my fraction exponents like this, as opposed to diagonally. It helps me keep things straight. One way to do it is I can take the square root, right? So that's what the bottom number means. And then I'm going to have 4 to the 3rd power. And if I evaluate this, 4 to the 3rd power is 64. And the square root of 64 is 8. So this is one way to do it. The other way to do it is, once again, realize that you have a square root here with that bottom number. But now we're just going to take the square root of 4, and then when we're done with that, then we'll raise it to the 3rd power. Now, the square root of 4 is 2, and 2 to the 3rd power is 8. So notice you get the same answer no matter which way you do it. The second method, though, is a little bit better. And the reason it's better is because if you do the power first, sometimes this number can get really, really large, and then it's kind of hard to take the root without using a calculator. So normally you want to do the root first and then the power second. Generally speaking, that's the better way to do it. Now, the second problem here is actually a little bit of a review question. We have 1/3 to the negative 2 power. So don't get confused when your exponent is a fraction versus when your base is a fraction. So 1/3 to the negative 2, this just refers back to the definition of negative exponents. What we can do to do this is just flip over the fraction 1/3 into 3 over 1, and then we turn that into a positive 2. And this basically is just 3 squared, and 3 squared is 9. And for the third problem here, we have 23.1 to the 0 power. This is a trig question. Of course, 23.1 to the 0 power is 1, because any number to the 0 power is 1. All right, and we'll end this section with just a couple more examples. So once again, we would like to simplify. In the first problem here, we have 25 to the 3/2 power. So this 2 in the denominator represents a square root. So we'll be taking the square root of 25. And then when we're done with that, we'll raise it to the 3rd power. Square root of 25 is 5. To the 3rd power is 125. For the second problem, we have 16s to the 4/3 power times t to the negative 3rd power. And we're going to raise that to the 3/2 power. Now we don't know what s and t are here, so what we're going to do with this is just simplify. So first thing I can do is raise 16 to the 3/2 power times s to the 4/3 to the 3/2 power times t to the -3 to the 3/2 power. And then we just have to work out each one of these. So 16 to the 3/2 is the square root of 16 to the 3rd. And then for the next part, right here, we have a power to a power. So we're just going to multiply these numbers together. So that will be s to the 4/3 times 3/2. And then same thing for the last part. We have t to the -3 times 3/2. So finally, square root of 16 is 4. So we have 4 cubed times s to the 2, right? Because when you multiply these together, the 3's cancel out and 2 goes into 4 2 times. So we have s squared there. And then times t to the -9/2. So this is 64 s squared over t to the 9/2. And for the last one, very similar. We have x to the -7/3, y to the 5/2, quantity cubed, divided by y to the -1/2 times x squared. So first things first, we are going to take each thing in the numerator and raise that to the 3rd power. Right, so that is what we do with this power here. And then the denominator stays the same for right now. Now let's work this out. X to the -7/3 to the 3rd power, we're going to multiply these together. Right, so we get x to the -7/3 times 3/1 times, and then we have y to the 5/2 times 3/1, and then divided by same stuff in the denominator. Now, -7/3 times 3/1, these 3's cancel out, so we just end up getting x to the -7 times, and then we have y to the 15/2, right? So all I'm doing here is multiplying these, and then divided by y to the -1/2, and then x squared. So now we can use properties of exponents. For these two, we can subtract the powers. So that's x to the -7 minus 2 times. And then for these, we can also subtract the powers. So we have y to the 15/2 minus -1/2. So this is x to the -9 times y to the 16/2, right? Because this is 15/2 plus 1/2. And this is x to the -9, y to the 8th. And the last thing we can do is we can drop the x to the -9 to the bottom and make it x to the +9. Now, I know I do some of these examples kind of quickly. Remember, you can always pause the video, rewatch it, etc. Most of all, make sure you get plenty of practice.